Whoops. All right. Okay, let's talk about the parameterized complexity of small decision tree learning. That's quite the mouthful. So let's split it up in two parts. The first part being small decision trees, and the second part being parameterized complexity. So small decision trees, what are they? So you might actually know them from this little flow chart we got at the beginning of the lecture that determines your grading schemes. And it looks something like this. And when you parse it in the mermaid syntax, you figure that it isn't a valid tree to begin with because it has too many paths that lead to the same vertex. We fix that, and we have the same thing here, and we have to do some arithmetic here. So we fix that again, and we end up with this tree, which is a perfectly valid decision tree where you have some input, which is like the grade of your presentation, whether you want to take an oral exam and your oral exam. And the output is your grade. In the Austrian system, it's 1 to 5, but with a binary classifier, it's as is the case with the paper, you just have positive and negative examples. So how it works is that we assume, or we try to find a perfect decision boundary with full accuracy. Otherwise, we assume that there is no decision tree. And we don't use any like entropy metrics or approximations. We just brute force through every single possible tree combination to find the one that we're looking for in this paper. And here we have the two interesting metrics. So the tree depth, 1, 2, 3, and the tree size, 1, 2, 3, 4, 5, 6, 7, 8. And these are low parameters, which keeps the tree interpretable. But as you have tried to model more complex data, the decision trees get harder to interpret. And ideally, we want to keep these two parameters low to have higher interpretability and performance, especially when you aren't trading off any accuracy. So in our case, it's optimal. But in practice, people are even willing to sacrifice some accuracy to have better generalizability of their decision trees. So this leaves us with these two problems, minimizing the size and depth, or more specifically, a decision problem where given some data or some examples and some size or input or depth, it is possible to have a decision tree that perfectly models the data. Our algorithm also returns the tree we found. So what is parameterized complexity? So you know that in the traditional notion of complexity, the decision trees have are NP hard, which makes them computationally intractable for super large inputs, but they become tractable as soon as we have like a more nuanced perspective and say that we introduce like some kind of limit to the size of some problem parameters. So the runtimes becomes polynomial to the input size, which makes it tractable, but exponential in some other parameters. So we kind of have like a more nuanced perspective on the input, which helps us determine which kind of the inputs are tractable and which kinds of inputs aren't. So in a moment, we'll get to how you find these parameters. But the three parameters that the authors introduce, one of which might even be redundant, is the solution size and depth, the maximum domain size, so how many values you can assign to at max to any of the features, and the number of features that any two examples assign different values to, which is the Hamming distance, which then makes these affect the runtime based on some exponential function, while the runtime stays polynomial in the input size. So how did they actually come up with these three parameters that made them achieve fixed parameter tractability? And how did they get from here, no parameters, to these three? So the approach is called the deconstruction of intractability. It's essentially just trial and error and trying to break the problem down into smaller parts that we observe have a strong influence on the runtime, which is just mostly through using algorithms and looking at the data you're dealing with in practice. The solution size is just from the problem definition. The number of values you can assign to each feature is determines your search space and the number of decision boundaries you can put anywhere. And the Hamming distance was actually found from the hitting set problem, which is where you try to find one set that has an intersection that is non-empty with a bunch of different sets in a collection in some universe. And it's small in practice for most data sets you see in the wild. So the proof of all of this is the algorithm. And it can be split up in two parts. I've written it down in Python, and I skip a lot of the notation, so we get to the core of it. So the feature selection part is pretty hard, but the tree construction part is pretty straightforward. So you take the features from the input, from the previous stage, and you return either a minimal tree that you found or null if you don't find anything. So how it works is, in this first function, find threshold, you have some tree structure, some feature assignment for each of the tree test nodes, and you return the thresholds that you assign to each of the tree nodes. And you do a binary search where for each of the nodes, you recursively try to find the largest threshold to minimize entropy. And this is what the authors say is based on the monotonicity property of the thresholds. But you can argue both ways. And then you just, after having found that threshold, you validate on the right child. And when you try to find the threshold, you recursively expand only on the left child. And this is another optimization. And this is what it looks like. So in the find threshold one, you call this binary search function. You checked whether the right subtree can't find a threshold and it succeeds, and then you check it for the left subtree as well. But this one can't fail because you've already looked up for the left subtree exclusively. And finally, how this looks like in practice is you enumerate all possible tree structures with the given size, and with some features as the input that you exhaustively assign to all possible tree combinations. So you enumerate all possible tree combinations and enumerate all possible ways to assign features to each of the decision nodes. And for each of these combinations, you validate whether a threshold exists. That's it. And for the feature selection part, so how do you actually figure out the features that you try to find trees for? Here's where it gets tricky. So essentially, we ignore the first part for now when you try to find the minimum decision tree. You generate support sets, and support sets are features that can distinguish most examples, and you enumerate all possible combinations of support sets given the examples. And for each combination of support sets, you call the minimum decision tree of a given size, and then you try to construct a tree with the given support set, as we discussed in the first stage. And based on the nodes, or based on the features that were used on the tree, you can then construct additional features that help to distinguish all examples. And then you create the greatest common denominator among these additional features, which we call the branching set. And this is the key to then construct the optimal or best tree. By then constructing this branching set and then recursively trying to add these features to it. And so here this is a super long function. I am going to omit it. Here you construct all the possible sets of features that help you distinguish most examples. And here's the little hack where you find this greatest common denominator among the additional features, which we call the branching set. Yeah, so time's up. This was a pretty like superficial overview of the paper, but nonetheless, I hope you found this inspiring. I hope that the whole way I implemented the pseudocode in Python made it more approachable, and I hope I inspired you to check the paper out yourself. And yeah, feel free to check my repository out as well. With all the code is open source, my report is open source, and yeah, thank you for your attention.